is to bombard the sample with infrared radiation. And then if somebody watched that video, tell me what happens when the frequencies of the functional group that's vibrating matches up with the frequency that's given off from the instrument. Somebody tell me what happens there. Because that's what it means to absorb the radiation. That's what it means. It means that the frequencies match up with whatever that frequency is that's being passed through that sample. When they match, that's when you get absorption. So somebody tell me what happens when the frequencies match. If you watch the infrared video that I sent. All right, we'll come back to that. So again, infrared is used for structure determination, to verify structures. You cannot submit a publication, a synthesis publication, without having the infrared data also published. Right, so you need NMR, you need infrared, and you need mass spec in order to publish a paper in a journal dealing with synthetic organic chemistry. So it's a great tool, again, for telling you what functional groups are present. We're going to talk more about that in a second, because again, every functional group has its own signature vibration, or its own signature frequency where it absorbs. And the thing about infrared, to kind of take the mystery out of it, is that when you have two atoms bonded together, they're not static, right? It's not like a model, like when you put two carbons together in a model set, and it's just sitting there. Those bonds are always moving. They have different types of molecular motion that they undergo. And so if the bond is like a spring, and between the two atoms, when you think about, and this is not going to show like it did in the video, but when you think about the two atoms moving, right, when you hit that bond, or that whatever that functional group is, with the right frequency, it's going to intensify the stretching or the vibration of that bond. So if the bond, let's say if the bond is vibrating at 400 megahertz, or 400 reciprocal centimeters, and you hit it with that same that same frequency or same wavelength of radiation, it's going to cause some excitation in the bond. So when the frequencies match between the bond and the instrument, then the bond gets excited, and that's where the absorption happens. Right. So when it absorbs that radiation and it matches the frequency of the bond, then you get a absorption, and then you'll get a stretch showing in the infrared spectrum. Right. So the wavelengths are 400 to 4,000. I think I said 0 on the first slide. Excuse me for that, but 400 to 4,000 reciprocal centimeters. And the wave number becomes larger as the energy increases. What that means is that as the bonds get stiffer and require more energy to cause them to vibrate, then that wave number is going to get bigger. So let's go back to the spectrum. So on this end, right, on this end of the spectrum here, these are high energy. Right, those are high energy vibrations down there. It takes a lot of energy to make those bonds vibrate, right, and match the frequency or the wavelength of the instrument. It takes a lot. And then down here, these would be lower energy. right? Lower energy vibrations on that end, because the wave number is smaller. That means it's a longer wavelength. And so it causes the wave number to be smaller. And again, the wavelength is normally measured in nanometers, but here is measured in centimeters. So again, it's 400 to 4,000. And then if you remember from general chemistry, the energy of a photon, that's how we calculate the energy for any type of electromagnetic radiation, is to calculate the energy of a photon, which is the speed of light times Planck's constant, right, times the frequency. Or you can also write it like this. So it's E equals H nu, right? Or H times C over lambda, because C over lambda is equivalent to nu. The frequency is 1 over the wavelength. So you can substitute in the nu in the energy of a photon equation with 1 over lambda, right? So that's why you can use either one. You use H times C over lambda, or you can use H times nu. But again, if we're measuring in reciprocal centimeters, then we want to use that C over lambda. We want to use the wavelength and not the frequency. So in the infrared, you have different intensities. You have weak intensities, medium, strong, variable, and broad. Broad, you'll see when you see broad intensity stretches, that's indicative of like an OH functional group, right? It's a very distinctive stretch, and it shows up in a specific region on that spectrum. But you also can have medium, strong stretches, variable stretches. It just depends on what the functional group is. And if it's a really strong stretch, you're going to see a really strong downward spike, right? A really strong absorbance on that y-axis, right? One of the things about infrared is that if there's no dipole, then you won't see any infrared absorption if you don't have at least a little bit of a dipole when you irradiate the sample, right? So something like this, like ethane, right? That's basically nonpolar and neutral. You won't see a you won't see a signal for that, because if it's symmetrical or if it doesn't have a dipole, then there's no signal associated with that particular functional group. All right. Any questions so far? All right. So let's look at just a few of the molecular motions that are possible. You can have stretching, and I know in the video I have this animated, but I'm not able to do that here. But you can have stretching where you can follow the arrows. These two arrows are pulling away from the central atom, and the central atom, when that happens, gets forced down. So that's one molecular motion. You can have bending, where these two are going away from the central atom, and then the central atom gets pushed up. And then you can have also twisting, right, where you basically flex these two atoms right here around that central atom. Right. So those are just a few of the molecular motions that are picked up once the molecule itself is irradiated. Initially it's just vibrating, right? But when you hit it with the radiation, it can stretch, bend, twist, wag. There's a bunch of different other molecular motions that are possible. But in order for any of this to take place, this is the key to the technique. The frequencies have to match. Now, that's not something that you do as a scientist running a sample. The instrument does it, because what the instrument is doing, when you put this sample into that instrument, it is bombarding that sample with infrared radiation in that range from 400 to 4,000 reciprocal centimeters. And when the frequencies match of the bond and the radiation that is being bombarded with, then you're going to get some molecular motion, some absorption, and then once that happens, you'll see a downward spike in your spectrum, right? So all of your functional groups have specific places where they show up, right? If you look right here, these are just some for alkanes, alkenes, and alkynes, right? So this CH stretch is a characteristic stretch of alkanes, right? And that shows up between, you're going to see this a lot. It's a really raggedy looking stretch between 2,800 and 3,000. And that's just for alkanes. Right? Then you can have an alkene CH stretch. And what that is this carbon-hydrogen bond just stretching away from the hydrogen, just stretching away from carbon, back and forth, right? That shows up here between 3,000 and 3,100. And then the alkyne stretch, same thing. This is pulling away from carbon. This hydrogen is, that stretches at 3,300. If you notice, the intensity is increasing because for the alkyne, this is sp hybridized. Right, what that means is that the carbon is more electronegative. So that CH bond is very short. So remember I said earlier, the bigger the number, the more energy it takes to get that bond to vibrate and to match, right, with whatever the frequency is being bombarded with. So it takes a high frequency infrared, it takes high frequency infrared radiation to get this bond to absorb. And so the shorter and the stronger the bond is, the more energy it takes to get that bond to vibrate, right? Or for that to get it excited, right? If it's a really short and strong bond. So that CH bond on the sp carbon on an alkyne is very short. Right? That's why it's higher. That's why it takes more energy to get that to vibrate than it does for the alkene and the alkane. And then over here, if we're looking at CC bonds, right? As you can imagine, a single bond takes less energy to get that to vibrate than it does for a double bond, than it does for a triple bond. Again, you can see the numbers going up from 1,200 to 1,660 to 2,200. Again, the carbon-carbon triple bond is a short, strong bond. So that means it's going to require more energy to cause it to vibrate. So it causes more energy for absorption to happen and vibration to happen because, again, it's a short, strong bond, it's very stiff. So it takes a lot of energy to get that to move. All right, questions? Any questions? So the take-home message from this part is the stronger the bond, the more energy it takes to get that bond to vibrate. The weaker the bond is, the less energy it takes to get that bond to vibrate. Right? That's the take-home message. So what we know about infrared is that the certain functional groups are going to show up in certain places on that spectrum. Just like right here, the 3,300, 3,000, 2,800. When you see those stretches, you know what you're dealing with, especially if you know the identity of your molecule, or even if you have an idea of the identity of your molecule, you can determine what's present based on the stretches that are there. So let's look through and look at some common stretches on the video. I think these were kind of faded in, but so right here, this is a broad stretch, right? That's my alcohol stretch. Every alcohol, the OH bond, right? There's a stretch pulling that hydrogen away from oxygen. It takes a lot of energy to get that to happen because oxygen is very electronegative and it's pulling that hydrogen to itself, pulling on that nucleus. So that's a short, strong bond. And it takes a lot of energy to get that to vibrate. So that broad stretch out at between 32 and 3,400, that is the alcohol stretch. And it always looks the same. It looks kind of wobbly and wide, right? That's always the case. Same here. Your carbonyls, those carbonyls always show up in a similar region, somewhere between 1600 to 1800. And I think I have that, yeah, here. But it's a really strong stretch, right? Very intense stretch. And you can see that right here. I have it highlighted, right? Very intense stretch. And while I think saw some more people come in, let me put this PowerPoint back in the chat again for people who may have come in late. Right. So your carbonyls, if this table gives kind of like a, because they're not all the same, right? They're not identical because there are a lot of different types of carbonyls, aldehydes, ketones, esters, acids, amides. So they all have different stretches, right? So this is for an amide, and this is just for the CO stretch, right? The oxygen, you can think of it as if you grab the carbon between your thumb and your forefinger, grab the oxygen and just pull them apart, right? That's what that means, that stretch. So the aldehyde stretch, 1740 to 1690, right? So there's a lot of nuance in there, depending on what's attached to that aldehyde. That's going to affect where it shows up on the spectrum. Your ketone stretch, right? 1750 to 1680. Your ester stretch, same 1750 to 1735. So this is one of the reasons why you can't use only infrared to determine the identity of a compound, right? Because you can see right here, a lot of these stretches overlap. They have overlapping numbers, overlapping wave numbers. So you can't just use this. This is used to confirm the identity, but it's not used as an initial identification method or characterization method. This is strictly supplementary, right? You want to, because your best method for confirming the identity of a molecule is NMR, not infrared or mass spec. They're complementary techniques. So this is a good example of why it's complementary and not simply the only method that you would use, because a lot of your frequencies overlap. And when that happens, you can't tell one thing from the other if you don't have any other information. So you can't determine the structure from infrared. You can only determine what functional groups are present. So I'm gonna put that up here. I'm gonna abbreviate compound. Right, you can only determine functional groups. You cannot determine the structure. You can only determine what functional groups are present. All right. You can't tell which carbons the functional groups are bonded to. You don't know any of that. All you know is that it's there. All right. Let's look at another set of functional groups, or aromatics. Look at where they show up here. How would you classify that stretch, especially comparing it to that nitrile stretch next to it? When I say classify, would you say it's weak, strong, variable, broad? What would you think? How would you classify that? If you had to describe it. Now look at the other stretches that are showing up.
Would it be a weak stretch since it's not stretching far?
Yeah, it's a very weak stretch. But look at where it shows up. It takes a lot of energy to get those. And this is, when it says aromatic stretching, what it's looking at is the hydrogens that are on there. Basically the hydrogens pulling away from the ring. Right, so it's like taking the ring in one hand, taking the hydrogen in the other hand, and pulling them apart. but it takes a lot of energy for that to happen. Now imagine if you had an aromatic and an alcohol in the same molecule, right? Those signals will probably overlap, and the alcohol signal will probably overshadow the aromatic signal, so you wouldn't be able to see it. So again, this is not a technique to determine structure. It's only to determine what functional groups are present. Right? But if you have functional groups that have similar stretches, then sometimes they may overlap with one another. You may be able to see one and not the other. It just depends. All right. So over here, this is these are just common stretches. So you're expected to at least have these if you don't know anything else. All right. So your nitrile 2000 to 2300, and that's a medium stretch because of the width. Right. It's not a very thick peak or a thick spike. It's a thin, but it is a little bit more intense than a weak stretch. So we call it a medium stretch. Right. Any questions about anything so far? Again, infrared is not, I'm saying not hard relatively, because the technique and the actual instrumentation is very complex. But the idea of what you're able to determine from it is a fairly simple idea, right? You bombard a sample with electromagnetic radiation in the infrared range. When the bonds in the sample match the frequency of the bonds and the stretching frequency of the bonds in the sample matches the frequency of the radiation, it absorbs it, and then you get a spike in that area, where whatever the wave number is. All right. Here, this is that big raggedy stretch that I was telling you about. Make sure y'all. This is your this raggedy looking, jagged looking stretch right here at 3000. This is your alkane stretch. Right, and then over here, compared to what we call the alkene stretch, 1400 to 1600 right here. Right, that's a very, it's medium compared to this one. This is a really strong stretch. Right, very strong stretch. But the alkene stretch is a medium stretch, and it shows up at from 14 to 1600. And as you can imagine, if it's closer to 1600 and there's a carbonyl present, it's quite possible that the carbonyl and the alkene stretch could overlap. Right, so again, you cannot determine the structure. You can only determine what functional groups are present. And sometimes signals overlap. You can't see one or the other because they absorb in the same region. All right, let's look at ethers. This is another very important stretch. This CO, sigma bond stretch. Sorry. Right here. Right, 1000 to 1200. It's a really strong stretch. So let me see if you are paying attention. Does it take a lot of energy for that to match the vibration of that CO bond based on where it is on the spectrum? Is that a high energy or low energy stretch?
Low.
It's a low energy stretch because it's closer to 400. Further away you get from 400, the more energy it takes to get those bonds to vibrate and match. And then right here again, you see this jagged, raggedy looking stretch right here. This is indicative of alkanes, right? CH, just simple saturated CH bonds, like this CH3 right here, right? That's what that is. That's what the stretch looks like. And it shows up at about 3000, somewhere between 2800 and 3000. Right, all I have here is a summary of the stretches at the end. And if you look at this structure right here, you can see that you have a alcohol, you have some alkyl chain, and then you also have the CO stretch, and you can see all of those. right here. That big broad stretch, very strong stretch. That's my OH. Right here. That's going to be my alkyl. Right, CH stretch, and then over here, right, that's going to be my CO sigma bond stretch. Right, so when you take an infrared, this is what it looks like, right? Unfortunately, we didn't get a chance to do infrared on our aspirin samples. But I think the group not last semester, maybe the semester before, right before COVID hit, we were able to actually go up, take our aspirin samples. We have 2 infrareds. Actually, we have 3. But it's a FTIR, Fourier transform. It's much different. The technology for infrared has gotten so much better because it used to be that you have to dissolve your sample up, put it on a salt plate, and put it into an instrument. Now with the FTIR, you can take solids and just put them on a disc, and then there's a diamond tip that goes down where your radiation is coming from onto the sample, and you can take it in open air. That wasn't the case years ago, but now they have much more sensitive and much more accurate instrumentation. Let's look at one more of these. Let's take this one right here. All right, so you have a carbonyl, which you can see here. You have an alkene. And then, of course, you got some alkyl groups here. Right, so this is, where do you think an alkyl stretching is? I'll let you tell me, based on what we've already talked about. The one highlighted in yellow, just the CH sigma bonds. Which one of those signals corresponds to that?
The one to the right.
To the right? What's the
Yeah.
number?
1620.
So remember that the alkyl stretching is here. It's in the range somewhere between 2,900 and 3,000. So right here, you can see that the alkyl stretching is going to be here. That's a high energy stretch. And it's very intense. And it always looks raggedy like that and jagged. So that's going to be my alkyl. Now at 1620, if you had to choose between 1620 and 1680 for the alkene, which one would you pick? 1680 is more in line with which functional group? Let's go back up. So we had an alkene in one of these right here. Is that right? Yeah. So you see the alkene is 1400 to 1600. And then the carbonyl is anywhere between 1630 and 1780. Right. So it's the alkene is a little bit, the carbonyl takes a little bit more energy in order to match that stretch than the alkene. So if you had to choose between those 2 signals, right here, which one would you choose as the alkene stretch?
The 1620.
Is this one? Oh, I'm sorry. You're right. I said alkene. I didn't say carbonyl. You're right. 1620. Good. And then by default, the carbonyl would be 1680. Sorry about that. So this would be a carbonyl stretch right here. All right, any questions about that? I mean, again, if you make a flashcard or a set of flashcards with these numbers on them, then that makes it much easier to remember those specific functional groups and where they show up. So let me switch over. We got about 6 minutes left. I'm only going to take 3 out of the 6. Let me go to here, right? Because we have some infrared questions on here. In addition to what we're going to solve with the NMR, which we'll start on Wednesday. And it's really important that you watch that video to prep yourself or read the section to prep yourself, but you got to do something. Because Wednesday, I'm expecting a little bit more participation. Yeah, right here. So for the functional groups here that are circled or highlighted or boxed in, and we got some numbers up here that we can choose from. All right, let's start at that carbonyl. Which frequency or wave number absorption value would you pick for the carbonyl? Out of 1700, 1680, 3500, and 1150.
The 1680.
Okay, let's think about that. You're right. That's a potential stretch for that. I agree. But we also got an alkene that we have to consider as well. So which one would be higher? The alkene, which is here, or the carbonyl? Which one would you think would have a higher? We just did that, as a matter of fact. So which one would have a higher absorption value?
The alkene would be right of the carbonyl, right?
So the alkene will give that 1680. And for this one, we'll give it 1700. Because remember, we just said that the carbonyl is a little bit more, it takes a little bit more energy to get that to stretch than it does for the alkene. All right. What about the alcohol? Which one would you pick for that? The OH stretch. You got 2 values left to pick from: 3500 and 1150.
I think the 3500 would go with the CH3 on the end.
The alcohol is the OH stretch right here. That's always going to be somewhere between 3000 and 3500. The OCH3, what we're looking at is this bond right here, the CO sigma bond. And the number that matches that is here, 1150. I'm going to go back through those because we got a minute left. All right, let me go back to that other, go back to here. All right, so you see like right here, your CO sigma bond is here, 1000 to 1200. That's the bond that's highlighted between carbon and oxygen. And then your alcohol stretch, that was the first one we did, is right here, between 32 and 3400. And it's always we didn't have the visual, but it's always this big broad stretch. But the number is always in this range right here, somewhere between 3200, 3500, somewhere in that range. All right, we're going to stop here. We're going to, on Wednesday and Friday, we're going to touch on NMR. So I'm going to send out the videos for NMR. And if you took Organic 1 with me last semester, then you've already been exposed to NMR because we actually we didn't do the work physically because the labs were still jacked up. But if you're taking it this semester, then you definitely got a chance to if you came in person on the days that we were doing NMR, you got a chance to do it. But we're going to stop here. And if you have any questions, just shoot me an email and then